So wanted to talk a little bit about both carbon-free hydrogen and renewable electrification in these high temperature processes. The whole goal is how do we wind up industrial, decarbonizing the industrial sector. I thought since we were talking with ITIF here, I'd start with what the conversation around ITIF often is when you're not sitting with the renewable energy community, which is about competitiveness, quite frankly. And so need to realize that this is a boundary condition for everything we wind up doing here. First and foremost, if you're working on new technologies for manufacturing, the manufacturing is just essential to our economy. Let's start out with that. About an eighth of our economy is, and this is the US economy, is still the manufacturing sector. For anyone that thinks that the US doesn't know how to manufacture things, we are still the second largest manufacturing sector in the world. Our manufacturing sector alone in the United States is larger than all but 6 economies, their entire economies in the world. So we actually do a lot of manufacturing here. It's also what winds up producing the products that winds up being consumed in the other 2/3 of our economy. So the products and services there. So the idea that, oh, this will just cost a little bit more means that the consumers at Walmart are paying a little bit more. So remember that everything, and we're making these technical trade-offs, that's a boundary condition. It's for what it is, it's there. It also employs many people directly. About 10% of our economy, of our employment base is in the manufacturing sector. And that's a foundation directly in the manufacturing sector. And that's the foundation of our standard of living. It actually employs far more people indirectly, both in the services, the IT sector. You think about companies like SAP, that their entire business is supporting the manufacturing sector, right? But they are accounted in the IT sector. Finance, logistics, all of these things get pulled in. It's also a foundation of things like national security and defense. Think about things like how do we manufacture vaccines? Big issues that wind up getting involved in it. It also uses about 1/4 of the energy of our economy, but it emits a huge fraction of the greenhouse gases in our economy. So this is a multi-stakeholder problem, no matter what we're trying to solve. It's also not a new problem. I think it's fairly timely. Since 1789, presidents with connections to Delaware have been talking about manufacturing. George Washington there sent a letter to the Delaware Manufacturers Society saying that domestic manufacturing is one of the first consequences to flow from an energetic government. So government involvement in manufacturing is certainly not new in the United States. So let's take a look at how we're doing on this. Over the history of the Department of Energy, where much of this work is done, you compare our energy in the manufacturing sector in 1976. Apparently they didn't have PowerPoint back in 1976 to make nice Sankey diagrams. But we used about 18 quads of energy, or excuse me, I've got this backwards here, the 18 quads of energy. I've got the GDP numbers backwards here. The 18 quads of energy in 1976, of which, if you look at the transition, and there's a certain amount of, back then they would not account the feedstock amount and counted that separately in the total accounting. But a big shift that we've had is actually decoalifying the manufacturing sector. It's probably the major thing that we've had. As a fraction, the amount of natural gas going into manufacturing, the amount of electricity going into manufacturing, and the amount of petroleum manufacturing is pretty much staying around parity at this point. The amount of coal going into manufacturing has gone down quite a bit. You can see this in all the little manufacturing towns that used to be along the Ohio River, that they're wind up having economic distress at this point. This also is tracking the energy and the related carbon emissions in the manufacturing production in the United States, not the consumption of the products. So don't think that this is that this reflects how we're doing in terms of society. We still have the largest consuming economy out there, and how we wind up buying things winds up affecting how things are manufactured. So that's got to be all linked together. So there's a lot of trade-offs. None of them are really good. This is a classic, what's called a wicked problem. You've got a lot of trade-offs, and this is an area that's ripe for technological innovation and very aggressive technological innovation. So look at all of the things we could do in the US economy, and we're trying to decarbonize the manufacturing sector. What would it make sense to do? and the most sense? Well, if you actually disaggregate by subsectors and by products, how much energy is used in each of these subsectors, and this is using the 2010 MEX survey. We can wind up updating it since 2010, but these don't change a whole lot. The two big dogs in the room are the chemicals industry and the petroleum refining industry. Huge amount of the energy used of the 25 quads of energy, it's almost half of that energy winds up going into those two sectors. If you also then track that relative to the carbon emissions, and it's a little bit the trade-off here in terms of on-site versus off-site. The manufacturing sector both uses electricity, but it also provides heat through combined heat and power to generate electricity. As an example, about a quarter of all the electricity in the state of Louisiana comes from combined heat and power from waste heat off of chemical plants. So, accounting for that CO2 is a little bit different. So whether you're looking at the on-site versus off-site energy consumption and total emissions, but this gets the general trend of where you're at. If you look at the three big things we're looking at in this meeting, we're talking about chemicals, we're talking about iron and steel, and we're talking about cement. Now, cement and iron and steel are smaller in the US economy because we're not building out new infrastructure. Frankly, we already have cities and we already have highways, right? So they're important industries, they're emitting industries on a global basis. And this is why this matters for the US, because the CO2 is the CO2 for all of us. On a global basis, they are much, much larger because places like, in Asian subcontinent and Southeast Asia are really going through a capital spending cycle. So a lot higher emissions there. And as noted, cement really does, you get CO2 just coming out of the Portland cement production from the chemistry that's happening there. Both iron and steel and forest products are actually below this average line. And you can think of that as they're going from the transition of, especially in iron and steel, from integrated steel mills of the US Steel and Pittsburgh days to mini mills that are substantially electrified, but as pointed out, the iron making part of that. So it's not the steel making part, but it's the iron making part that really does need to be, how do we get the carbon out of it? So those are some of the challenges you wind up having. Then one of the things DOE does is they do these bandwidth studies, and what they go around and they say, okay, how much energy is consumed, and they are energy related, not CO2 related. We can go through and look at the energy related and say, how much energy is used, say on the chemicals basis here. These are sector at a time. And what's the total amount of energy used in that sector? And then you look at what the most energy efficient plant is in that sector that's currently deployed. So current deployed economic technology, and said, if we transferred all of our existing technologies to that current technology, in other words, decommissioned all the existing manufacturing plants that are less efficient and then applied the new technology on it that's cost effective, you'd actually reduce your energy consumption. Why do people not do that? Well, energy cost is about 8 to 10% of your marginal operating costs, or capital expenditure, building those factories and recovering that cost is a huge number that's there. The next issue is looking down and saying where the research and development potential is, where there's at least one published paper saying, a new catalyst or something like that for doing a chemical. And if we were to mature that technology all the way and get it deployed across the entire economy, how much energy would be used is at this point. And then if you wind up going all the way to the point at the left, that's actually the sum of all the Gibbs free energies, or as Addison on the line here would call it, exergies of the processes that are present. And the chemicals industry is fascinating because it's the largest energy consuming sector. But if you added up all the chemical reactions, it actually should be providing energy to society. So that's a really, it's interesting to look at how those wind up going through. There's a diversity of challenges trying to figure out the solution on manufacturing, though. Typically, the conversations go down to the point of saying, let's go all in on the most promising solution, instead of saying we need a portfolio of solutions. I would advise against that, because this is a portfolio problem. There's also no single cost target for development, because each cost and products are at different price points. And as we'll point out in the next slide here, following up on the basic undergraduate economics, if you wind up having an increase in the cost of your supply, you'll actually have a decrease in the demand, always. That'll put someone out of work, by the way. Someone is not going to work doing manufacturing as a result. So if we just internalize the cost of carbon, that's what would wind up happening, for good or for bad, but realize that's what would happen. And you wind up getting a lot of political pushback. The other thing you look at is say, well, why don't we just identify these ideas here on the upper left? That's the price that a consumer would pay for a carbon-free product, whatever that product is. And let's go after that as our early targets. Well, when you wind up doing that, realize the difference between price and cost is profit. You're literally telling them to take less profit. So you're working against the targets of just basic economics on this. So what you really need to do is figure out what those commodity prices are. And those average commodity prices I've listed over on the left here. It's a range of prices. It's not a single number because your feedstocks go up and down. A key one here, as pointed out before, was in separated hydrogen that you wind up getting as separating it out of syngas from steam methane reforming as a process. This goes into petroleum refining. Not only is it desulfurized, but you sell petroleum by the unit volume. And frankly, putting hydrogen in hydrogenating gasoline swells the petroleum. So you actually get more money for the cost of making the hydrogen in there. This is also the cost at the incumbent technology price. So I always put down here, this is $2 a kilogram to $1.50 a kilogram. You're going to, if you develop new hydrogen technologies, get an erosion in that price because they're not just going to stand still on the methane steam reforming world. They'll probably get a 50% cost reduction just because they've got competitive forces in place. So you need to look at saying where hydrogen prices are going to be, what's their entitlement price, not what's their current price. So that's going to be a challenge in terms of setting very aggressive price targets in these hard to decarbonize high temperature sectors. Then the other really hard part is that what is your cost price? And I'd like to point out there are actually 3 crossover price points you need to get to. You have crossover parity, which there was a little bit of a sidebar discussion in the chat over why don't steel companies just go to the newer technology if it's lower cost? Well, they've already built infrastructure. And so if you're only talking about building new infrastructure for new technologies for increased demand, then you're looking at just cost parity crossover price. Demand's fairly constant. So that's a long time to transition to make that wind up happening. A more aggressive cost price is actually where you're looking at your transformation crossover parity. And this is what's happening to coal-fired power plants right now relative to relative to natural gas plants. That is that the all-in cost for the new technology, including the depreciation and amortization of new equipment, is less than the marginal operating cost of operating a fully depreciated, already existing plant. At that point, it literally is cheaper for a manufacturer to just switch over. Make that the cost target you're shooting towards. Even if you don't get there, make that's the target because that's what you need to get to. And teardown cost parity is literally the point where the new technology is more valuable than the all-in cost of, or the marginal operating cost of the incumbent technology. And in fact, the real estate where you're at is more valuable than having the facility still standing. I show the picture there of last year, Bethlehem Steel's former corporate headquarters being imploded because the real estate value was more valuable. So that's even more aggressive as a price you get to. But having that transformational crossover parity is a key point to wind up getting to. Some key reactions to look at on this, some categorizations on it. It's the iron making and steel making, it's the cement production, it's ethylene cracking, and methane steam reforming, if you're looking at hydrogen, is the key one to wind up looking at. It's not that high of a temperature relative to some of these other temperatures, but it's the basis for all of the other processes, because this is how you take methane and they make hydrogen today at $2 a kilogram or $1.50 a kilogram. So that's the price target you need to get to. By comparison, not only looking at hydrogen, but looking at heat, is what are pathways to clean, sensible heat. Heat is the big amount of energy that goes into the industrial sector. It's a lot of products that are there, but about process energy is more than half of the total energy that goes into manufacturing sector. And from that, fuels for process heat, direct process heat versus cogeneration fuels and things like that for on-site generation are where your big target is. So dealing with having fuel converting directly to process heat is the challenge that you'd have. So what's the price target for that? Switching from talking about hydrogen, but talking directly to solar, to renewable electrification. The marginal operating cost you're looking for in transforming to renewable electricity, and that is the all-in cost of taking renewable electricity and turning it into heat, is less than the marginal cost of discovering the next little bit of natural gas that's out there. So what do I mean by that? If you look at the price of natural gas, not the cost, but the price on it, when it gets below about $3.50 or $4 an MBTU, typically the rig count goes down. That's to say that the oil and gas producers can no longer afford to find more natural gas. That is the inherent cost of natural gas, or the steady state price should be. The price can dip below that because once they've discovered it, they can sell it, right? But don't just follow the price on a daily basis. Follow it on what's the cost to discover the natural gas that's out there. If you wind up running through the numbers on that, it turns out that if you wind up taking renewable electricity and turn it into heat at some efficiency on that, versus taking natural gas and turning it into electricity and turning it into heat, when you get to the point where you're about $10 to $15 of a megawatt hour electricity, this is 24/7, fully firmed, all storage, all capital costs involved of renewable electricity. At that point, it'll make more sense to just take renewable energy and turn it into electric heat. That is a really aggressive cost target for renewable plus storage. But if you actually look at the cost trends we're on, somewhere around 2030 to 2035, we should hit that crossover point. But you need to get renewables plus storage to be dirt cheap. They're about 20% of the cost of where they are now, or the price of where they are now. So we've got line of sight to that. Keep investing in those areas. That's the strategy. So the strategy for renewable energy plus storage, electrifying the manufacturing sector, the strategy on that is storage and renewable energy. Get those cheap. The manufacturing sector already knows how to turn that to take electricity and turn that into heat. Problem is, how do you get electricity cheap enough? Getting hydrogen cheap enough is another thing. So if you look at the current targets that we have, the recently published industrial uses is target for hydrogen is stated at being $1 a kilogram. I completely concur with that $1 a kilogram target should get to, but there's not a lot of specifics on how to get there. And in fact, if you look at the DOE hydrogen program, their 2020 hydrogen program case study they look at gets them down to about $1.77 a kilogram. That's not going to get there. So in the hydrogen area, if there's one thing I would target is saying we need a hydrogen shot, just like a sun shot 10 years ago. Set $1 a kilogram as the target to wind up getting that carbon-free hydrogen and decarbonizing the manufacturing sector. Until you wind up getting to those low prices, so both for renewable energy, for renewable electricity, or for carbon-free hydrogen, you're fighting economics along the way. Don't be afraid of having some aggressive targets out there. Clearly look at why there might be some laws of physics that might limit the ability to get there, but we need an aggressive target and get down to that price point. So again, this is just a summary here. What I've said, there is no silver bullet on it, because the manufacturing sector has a lot of stakeholders and a lot of needs that support society. If we want to wind up decarbonizing it, we need to be aggressive and really drive those two areas of clean, firm renewables and clean hydrogen at very aggressive cost targets. So with that, thank you very much.